with this more on term symbols. And I forgot that I also have this other PDF, another guide on how to go through term symbols. And I'm going to post this on the Canvas course. But this just walks you through all of those rules that I just went through. So this will be another good reference for you. And so as you scan through it, here, right, it's showing you that we can calculate it in terms of the mLs or in terms of the L values, right? It walks you through the Clebsch-Gordon series. It gives you the designations. What I wanted to do, though, is scan through to give you more of this information on those J values. Let me find that example right here. Aha, okay. So here it walks you through this example, just like what I did, where you get all of these crazy possibilities when you start including those J values. So for example, when you have a triplet D, then triplet D3, triplet D2, triplet D1 all become possible. So which of these terms corresponds to the lowest energy state? Well, we use Hunds rules to determine. And so I want to review those Hunds rules really quick, okay? So the state with the largest value of S is the most stable. So let's just talk about that for a second, okay? So S gives us multiplicity, right? And the largest value of S, for now, what we've discussed corresponds to a triplet state, right? Because S is 1 for triplet state, and 2 times 1 plus 1 is 3. So triplets are more stable than doublets, which are more stable than singlets, okay? For states with the same value of S, the state with the largest value of L is the most stable, okay? So if I go back to this list here, so all of the triplets are the most stable. So the triplet D, the triplet P, and the triplet S. Well, the one with the largest value of L is the most stable. So the triplet D will be lower in energy than the triplet P, which will be lower in energy than the triplet S. Okay? So continuing along. And so that's if they have the same value of S, right? If they have the same multiplicity. So if states have the same value of L and S, then for a subshell that is less than half filled, so we got to think about this, less than half filled, the state with the smallest J is the most stable. And I already gave you an example of that, the sodium doublet lines. Sodium is exactly half filled, right, with the 1s1. And certainly when it goes into the 3p1, it's definitely less than half filled. Well, the J1 half state for sodium was lower in energy than the J3 half states, okay? But for subshells that are more than half filled, the state with the largest value of J is the most stable, okay? So if we now kind of go back to all of these examples, you know, we don't know which ones of these are half filled or more than half filled. So we don't know. So that's once again where having the electron configuration is really useful, okay? So let's go through some of these examples. And so here that you can see how they list this, right? We note that the triplet D was the most stable, triplet P, then triplet S, and then it starts over again with the singlets, okay? And so now, so it says, since 2p subshells are less than half filled, we would predict the triplet D1 term corresponds to the most stable state. So that's because they, in this example, I lied. They actually did, they did give us that electron configuration, okay? So let's go through some of these examples for simple atoms. And I'm just going to pick out a few of these. And I would recommend that you try the rest on your own, because I'm just going to flash forward here. I've got a cheater periodic table that's got the periodic table with every single ground state term symbol. Lovely. Okay, let's go through it. So I like to go through oxygen because that's something, that's a term symbol I've actually already given you. We talked about this in Chem 361. So let's do it. So I'll remind you that it goes 2s plus 1, L, and J. And here, luckily, we have the electron configuration, so we're all doing ground state. So we note with the oxygen, I'm not worried about the 1s or the 2s because that's all going to cancel out. And then now with the 2p right here, okay, I'll kind of do my work over to the side. So here with the oxygen, my mLs, right, are -1, 0, and +1. So I have 2 electrons in this -1. So that's going to go -1, -1, +0, +1. And all of that equals -1. And the absolute value of -1 is 1. And that gives me the p term. Okay? No other possibilities. No Clebsch-Gordon necessary because I have the electron configuration. Okay. What about the multiplicity? Well, if we were to go and add up all of the spin states for this thing, we would in fact see that we have 4 electrons to consider, right? But these 2 electrons, they're paired up, and they're going to give me an s equal to 0. So that pair is going to cancel out. So what I have going on right here, I have 2 unpaired electrons, and those 2 unpaired electrons definitely correspond to a triplet state. Okay? And so I'm just checking my notes to make sure. Yes. So, because right, that would go 1/2, -1/2, which would cancel, and then +1/2 and +1/2 to give me 1. 2 times 1 plus 1 is 3. Triplet. The other thing to recognize is when we see 2 unpaired electrons like that, even though we have a paired state, the paired state is going to cancel out. So you could really just look at this and see 2 unpaired electrons. Automatically, that's got to be a triplet. Okay. Now, what's the appropriate J value? Well, we know that J, let's back up and look at that for a second. J is L plus S all the way down to L minus S. All right? So if S is 1 and L is 1, we could have triplet P2, we could have triplet P, or triplet P1. I think that I made a mistake on this. So when S is 1, oh yeah, 1 and 1 is 0. Okay, good. So yes, all of these become possibilities. Triplet P2, triplet P1, triplet P0. So which one is it? Well, if the state, let's see here. Okay, for subshells that are more than half filled, state with the largest value of J is the most stable. So that means my ground state here on oxygen would be triplet P2. But oftentimes we see an oxygen atom just listed as O triplet P. Hopefully maybe you remember that from our kinetics. Because that J equals 2, that non-half integer state is less important for the spectroscopy. So we would list that as O triplet P. Okay. So